They're both cool. Ziegler and Harvey are cool. It's on the record. Anyways, okay. So for all of us, this is a recap. Revisiting this this proof and this theorem. And what I tried to do is relate it to something that we are already familiar with, and that is similar triangles. Okay, and so I'm going to outline these two chords. Outline those two chords. And so we know that between any 2 points there exists exactly one line, so I can play connect the dots and make this diagram. And so if you were told that this angle and that angle were congruent, then you could conclude that vertical angles are congruent and then these two triangles are similar by angle-angle similarity. And if that's the case, if two triangles are similar, then their corresponding sides, or side lengths, are proportional. And if two things are proportional, then you can write a proportion relating those two ratios, those corresponding lengths. So what you have to make sure in this diagram that you understand is what sides are corresponding with one another. It helps you when you have those congruent angles marked, because then you can clearly see, okay, this side, whose length is labeled by D, that's in between the angle that has one mark congruency and the angle that has two marks of congruency. So that's going to be corresponding with the side in the other triangle that has the same marking. And so this side length that's being represented by B, that is being formed by the angle with one mark congruency and two marks congruency. So from the small triangle, D is going to be corresponding to B in the larger triangle. So we're going to write another ratio, compare the other two sides. A from the smaller triangle, because that's what's on top, is corresponding to C, the length of that other side. And then we can take the cross product of this, and we know that when we take the cross product, it's just going to produce another true equation, another true statement. So A times B, and the product of A times B is equal to C times D. So this is absolutely true. And so when we look at it and we apply it to circles, these angles are congruent because they're vertical angles, and there's no questioning that. Vertical angles are always congruent. However, when I first started this, I just said, what if you knew that this angle was congruent to that angle? Well, we do know that because in this realm, when it deals with circles, both angle D and angle B are inscribed angles, and both of the angles are intercepting the same exact arc. Remember that the arc that lies in the interior of the angle, that's the intercepted arc. So this angle, it is intercepting, these two angles are intercepting the same exact arc. If that's the case, they have to be congruent. That's one of the theorems that we learned on the third page of our notes at the very bottom. So we do know that those angles are congruent. And so we can just apply this. And so if we notice that A and B, those are the two pieces of one chord. And so we're taking their product. And then C and D, that is the two pieces of the other chord. And we're taking their product. And those will always equal. These two chords are being broken up into two pieces because they're intersecting. So that point of intersection right here, point X, that is what separates these chords into pieces, is that point of intersection. And if you take the product of those pieces, they will always be equal to the other product of the other pieces of the chord. And so we then moved up and looked at that theorem. And the theorem, that's what you'll find in a textbook, in our textbook. It's very wordy. And it says that when two chords intersect, the products of, and this is where they get really wordy, the product of the lengths of one chord. They're talking about those two pieces, the lengths of the segments of one chord. The segments are now the two pieces of that one chord. And it says is equal to, and then again it has this very wordy description of the pieces, the lengths of the segments of the other chord. And so this is my way, this is how I remembered it. I just try to simplify it and say, hey, take the product of the two pieces of one chord, set it equal to the product of the other two pieces of the other chord. So here, this is one chord. It's being broken up into two pieces, 6 and X. I'm going to take their product. And that is equal to the product of the pieces of the other chords, 9 and 12. 9 and 12. And that's a very easy equation. We can solve that. Just say, well, this is 6x equals 108, so divide by x, or sorry, divide by 6, and we get 18.
Yes.
That's what our homework on page 343 is all about, and 44 and 48. So having revisited that, let's look at the problem on Springboard page 343. And it's this guy. So it says, in the circle shown, what is the measure, what is the value of x? Show your work. This point of intersection, we don't know if it's the center of the circle. We can't make any assumptions. So, if you have the lengths of these pieces, then you just apply that theorem. That the product of the pieces of one chord is always going to equal the product of the pieces of the other. So we have that x squared, because that's what x times x is. The product of these is x squared is equal to 196. And then what do I do from there if I have x squared? Square root it. It's exactly 14. Alright, move on to the next one. 344. It says determine the value of x and y. Okay, right now, can we solve for x? No, we need y first. So let's solve for y. If you ignore all this nonsense here, even the 90-degree angle, you've got two chords that are intersecting. And so product of the pieces equals product of the pieces. So the two pieces of this first chord, 20 times y, that's going to equal the product of the other pieces, which is 16 and 16. So we've got 20y is equal to 256. And then we're going to divide by 20 on both sides. And so we're going to have 12.8. Cool. Okay, this is going to make our x value a little icky. So how are we going to solve for x now? Pythagorean's theorem. Okay, Pythagorean's theorem. Because x is the length of this chord here, which is the hypotenuse of that right triangle. Okay, so I don't think we need to practice on Pythagorean's theorem. And plus, the fact that we have this decimal, we're going to get the square root of another decimal, and we haven't quite talked about how to simplify those radicals. So since we have almost no one here, we're not going to do that today. I don't want to go over it again. But yes, as long as you know that you would need to use Pythagorean's theorem to solve for x. Is there anything special about the chord that's in blue ink, or the chord that's in red ink? They are perpendicular. Mm-hmm. What about as individual chords, individual segments? Say that louder. Why would the blue one be a diameter?
Because it's bisecting the red chord into two curved parts.
Okay. Turn back a page. This diagram, that one was bisecting this chord. So you're saying this is also a diameter?
Oh, no, never mind, sorry.
Well, let's keep rolling with it. Let's keep rolling with this.
Because it's perpendicular and it cuts the red chord into two congruent parts.
There you go. Okay. It's
It
both
makes it
perpendicular and
Right.
bisecting. And that's the theorem that's on the second page. Second page. Yeah, it's on the far right. Yeah, it's on the far right. And it says when a diameter is perpendicular to a chord, then that diameter bisects the chord. So we have a variation of this, what's happening. We have a chord that is the perpendicular bisector of another chord. Well, if that's the case, then that chord has to be a diameter. So, yeah, you can prove that that has to be the diameter. Okay, sweet. 348. Number 10. Lots is going on in this diagram.
Did you ask what's going on or
I
lots?
said lots.
Okay.
Yeah, lots is going on.
I'm sure I didn't misunderstand.
We have this red chord there. We have this red segment here. What is that? Or sorry, green.
Radius.
That's a radius. And then we have got. I'll do the blue. We have another chord here. Okay, we'll go one at a time. The red chord. Is there anything special about that one?
Diameter.
No, it is a diameter because they've got that dot. And so that is a diameter. And this diameter is perpendicular to the blue chord. So what's happening?
It's bisecting it.
Means that blue chord is being bisected by that theorem that we just got done talking about. Okay? So we should be able to apply this product of the pieces equals product of the pieces. The blue chord, the two pieces are x and x, and we should be able to set that equal to the product of the pieces of the red chord. Well, I know that one of the pieces is 2, but we need to figure out what is this length. How do we go about that? Because we can't have two unknowns. We can't have x and then another variable like y that's representing that length. We can't have two variables.
It's 6.
Why is it 6? Because you have the radius.
So the total is 8.
Okay, there's a bunch of ways that people are going about this. If you know that your radius is 4 units long, then you know your diameter as a whole is 8 units long. And so we just subtract the 2 away, we get 6. Some other people are saying, well, this is a radius, so I know that this section is 4. This is also a radius, so I know that that is 4. Minus 2, so that has to be 2. So 4 and 2 is 6. However you went about it, yeah, it's 6. So this would be times 6. And so we would get that x squared is equal to 12. That means that x is equal to 2 square roots of 3, which is b. So there's a lot going on in that one. There was radii, there were diameters, there were diameters that are perpendicular, bisectors of other chords. That really kind of just brought everything together about chords and diameters and radii and circles.